cool. Yeah, so this isn't my specialty. I was trained as an analyst in grad school because I took abstract algebra and I had no idea what was happening. This stuff is weird. It'll be one of the strangest classes you'll have had in your undergraduate career. Guaranteed. And it's going to involve new ways of thinking that may or may not work for you. We'll always work together to make sure that, we just work together to get A's, right? Like these two know me. They know how I roll. You don't, Kyle, but we'll just all work together to make it easy for everybody. So let's get rolling. First thing, let's just take a minute. I don't know if you dread this or not, what's about to happen. So usually start with just a little check-in. So we just take a minute. So just everybody, just close your eyes for a second and just feel what you're feeling. What is your body feeling like? What are you noticing right now? Try to bring this to sensations as opposed to your thoughts, which might be all over the place. If you were a scientist, you were tasked to write a report on what you're feeling. There's no wrong answers. This is good science. We won't do this long today, but we might add a little more time as we move along. So just come on back gently. And it's nice to have that little reset. It primes us, it's like tilling the soil, the math soil. So let's start off with a handout, a color handout. Cool. Yeah, exactly. Pay the big bucks. This is what you get. So this handout I will put up online, Sydney. It's this one right here, whenever you watch this. Let's take a look at these objects. And I'm kind of eschewing all the formalities like the syllabus. We'll get to that. Let's just start having fun. That shit's like there. We'll get to it soon enough. So, anything you notice on this page? What do you notice? You just notice stuff about your body. What do you notice here?
A couple of these kind of look like chemistry stuff.
Totally. Definitely that, yeah, absolutely. Those molecules at the bottom.
Yeah.
The red one is H2O, and then the other one is ethane, I think.
Not sure.
Okay, we don't have any chemists here.
I'm getting into it now. But
Okay, but I'll just say it's ethane. Nobody can say it's
yeah.
not. So yeah, okay. So that's ethane. I'm pretty sure it is. Yeah, cool. That's a good thing to notice. Is there anything that maybe they share? They look really different. Is there any sort of salient property, abstract property?
Symmetry.
Ooh, nice, Diana. Absolutely. There's a lot of symmetry on this page, right? So, for example, this top left one. What kind of symmetry does it have? So let's talk about what symmetry means first off. How can I move myself so that I land back in my original state? So how can I manipulate that shape so that it lands back on itself? What are some ways? Let's just start with that top left one.
rotate it.
You gotta rotate, yeah. How many different rotations are possible? Up to like 360 degrees, kind of, so that we're not repeating ourselves. How many different rotations do we have? That's a good starting letter.
Yeah.
Nice.
Six. At 6, I think the 7th you would get back to how it is.
Yeah, is that right? Yeah. Wait, so you got me wondering. So it's a good here. So the top thing can go 1, 2, 3, 4, 5, 6. Yeah, and then back to 7. So we could consider, we could say 7, where one of them is a non-rotate. I don't do anything, and it stays the same. So for this one, we've got 7 rotations. Anything else you could do to it?
Probably flip it over.
Absolutely. Lots of different potential ways to flip this, but there's a really nice one where you go through one of the leaves down the center, and then it comes out between 2 on the other side. So I'm just drawing a dotted line through the center. You see what I'm talking about, like with that?
I don't know if you can read that.
Yeah. So how many of those are there? How many ways are there to flip like that and land back on ourselves? Yeah, there's 7 essential flips, right? Cool. What about that next one that's to the right, the red saw blade thing?
You can also rotate that.
Yeah, how many rotations do we have on that one? I gotta count you. Counting the no rotation as a rotation. 12. So 12 rotations. Do we have flips? So that last one, that was, you could see that we could just kind of get mirror images kind of stuff. Is there mirror imaging going on here? I could draw a line maybe straight through, and I can get opposite. I could draw a line right through points, sharp points, right? And go through the center because we have that nice even number. If I flip it over that line, is it going to look the same? No. Because there's actually kind of an orientation here, right? With the way those things are overlapping to the right. And so if you flip this, you get a mirror image, which is not identical to the original. So this one has that rotational symmetry, but no flip symmetry at all. You can start to see the game here. Yeah. What about this next one? The cool, looks like a Celtic thing almost, of some kind. Three whats?
Rotations.
3 rotations. Any flips? Yeah, I like that you're rotating the page, Diana. Why not, right? We got it. Yeah, let's do it. And you can imagine flipping it by kind of, just doing this, looking through the page, a little bit of a cheat. I can kind of see it there. Or I can give you another one, if that would help. I might have another one. Maybe I don't. Can you flip that one over? Can you pick it up out of the page, flip it over, and have it look the same? Can you see mine through there? Does that look the same as that one? It's hard to see, but.
No.
Doesn't, what's different?
You can look in the center here, and it's coming up around this way as opposed to.
Yeah, exactly. So there's definitely, is that making sense that there's an orientation to this one and that its mirror image is not identical at all? Cool. Dartboard, what's up with that? That's a great question. What if we do?
You can't do anything.
There's no symmetry, right? Yeah. If that's part of the image, otherwise, what kind of symmetries do we have? Let's say the numbers aren't there, we fill them in.
Yep. So the only thing I'm doing is removing the numbers essentially from.
You can rotate it then only 10 different times because you'd have to rotate it 2 spots over.
God, yeah, nice because of the red-green alternation, right? So that kind of. Do we have any flip symmetry?
Yeah, I think so.
How many flip symmetries are there? There's 20. So this one's really interesting, right? So we have, it's kind of hard to write that all down, but making sense? Groovy. What about that cool little wallpaper pattern thing, like a runner or something? And what I would like you to imagine is this goes on forever in both directions. So I'm putting a dot, 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 which I should have put on there, but that is an infinite strip.
I mean, you could keep sliding each of those things, the entire thing, like entire piece of it. I don't know what I'd call the. So like not all the overlapping pieces, but the big chunk. You could slide that over.
Yeah, like if you just took the whole strip, right, and moved it,
Yeah.
it can land back on itself. It's hard to say, it's hard to describe precisely how to do that, but notice that the pattern repeats
Yeah.
left to right. There's like, I think it's what you were talking about, Kyle, there's like this little major chunk,
Yeah.
right, that repeats. It's like somebody took a cookie cutter and boom, 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 left and right. So if I shift that thing left or right, the appropriate amount, or in multiples of the appropriate amount, it lands back on itself. So here we've got a whole different symmetry that we didn't really see in the top ones. It's this kind of a glide symmetry.
Yep.
You know? Any other symmetry that we have seen before?
Yeah, you could rotate each individual trunk.
Well, we got to move the whole thing, so we can't.
Oh, okay.
Yeah, we don't get to.
Not the individual trunk.
Yeah, so this whole thing is kind of a locked
Okay.
together piece. Could I flip this? Could. Does this have a flip? So let's see here. So I've got, let me get the board. Let's get up on the board here. So let's look at that main chunk. The main chunk goes, we got, oh God. I forgot to bring my super stash of awesome markers, but I won't. This will teach me. So we got that. And bear with me on this, please. This is meant to be the same thing here. Kind of like that. And then this guy goes like that. And then like that. Right, so that's the essential piece, more or less. If I flip that, like over this line, is it going to land back on itself? Not really. So I don't really have that flip symmetry here. No matter where I flip, that's not going to go. What could I do to that shape to make it land back on itself? So we've talked about it, and it's not a flip. And it starts with an R. Yeah, rotation, right? So if I literally take this thing and rotate it, how many degrees? 180. So notice this has a rotational symmetry of 100. So I've got two rotations. First one lands it back on itself, then I could rotate it back again, and I'm actually where I started. But so this one has two rotations and glide symmetry. This is something we actually won't spend any time on this semester, but I wanted to point out that there's going to be symmetries beyond what we talk about in here. All right, that H2O molecule, there's some clear symmetry there, right? And you see one of the axes of symmetry, so I could kind of flip it over that axis that's running through there, so I've got a flip symmetry on it. I've got a rotational symmetry, but it's not very interesting. I could rotate it around imagine an axis that is perpendicular to that one, you know, so we've got, what do we got? We've got that bond there, and then this bond coming out here. And we've got that, like that, and okay. Right, I could put an axis down through here and rotate it like this, but I have to go full 360 to get it back on itself. So it's not super interesting. Everything rotated 360 degrees lands back on itself, unless the universe has gotten really weird. And then this other one, this ethane molecule, is way more complicated, right? There's a lot going on here, and once we add this third dimension, which we're trying to represent here, things get very intense. So lots of rotational symmetries here, flip symmetries. Can you kind of start to like piece those out? Can you see the flips? Well, actually, oh, there is a flip, isn't there? Do you see the flip? It's kind of weird. Yeah, for a minute I thought there wasn't. What's the rotational symmetry around the main axis? What do you have? I'm sorry, go ahead. What was that, Kyle?
120 degrees.
Yeah, definitely 120. Yeah, absolutely. Here's an interesting little trick. What if I rotated 120 and then flipped over that? Now let's not get there yet, sorry. It's too high, I don't want to deal with this thing. Anyway, what about that last, now you can see we're coming home stretch. What about blue whatsagon? I don't even know what it is. Septagon? Sure, yeah, seven-sider. What kind of symmetries we got?
It's a heptagon. Not that that matters.
Does it have to? Let me look it up. Yeah, it might.
I think it is.
Hexa, there's hexa 6, right?
Yeah. Octa's 8.
Octa's 8.
Deca's 10.
Totally agreeing with all that. It's what is it?
It's
Heptagon.
Yeah.
Wow, what's septagon? It's like septic tank. I like it.
I don't know if it's a thing.
I don't think it's a thing. Can you look up septagon, please? Nice, Kyle.
Sounds like a trans.
It sounds like something, right?
It just, actually both names are right.
Oh, really? Okay.
Ooh!
It's because sept is the Latin prefix, and then agon is the Greek suffix, and so you can either do heptagon or septagon.
That's pretty cool. I did not know that. Now we learned something super unexpected. So you see here we've got 7 rotations around the center.
Yep.
And do we have a flip symmetry? Yeah, right. Through a corner and then the adjacent side of that. Yeah, we've got 7 of those. So this one has 7 rotations and 7 flips. In some way, this is the same as the first one we looked at, right? So they share a symmetry here. In some ways, they are alike, and they are unlike everything else on this page. What about that final, the circle at the bottom? What do we got there? Lovely. Assume it's a circle. It may or may not be within some kind of tweak it was intended to be. Infinite, yeah. Infinite rotations and infinite flips, and it's quite beautiful. It's like a perfect symmetry, right? So that's what this class is about, symmetry. And all these things are accessible. That's why I put them on this page. These are all things we can look at and literally understand. Now, if I told you I had a 1,000-sided solid in 7 dimensions, it sounds, yeah, very cool, right? It's like, let's talk about that. I can't put that on this page, but by using the methods of this class, I can own it and I can understand it in terms of how does it relate to itself through some simple motions. I can understand symmetry of things I can't picture. This class might as well be called abstract symmetry. And that's what it's all about. You've done algebra, you factored polynomials, and all those skills will mostly come in handy. But what you're going to have to do is forget them. Because you're gonna wanna do all sorts of things you're used to doing, and they may or may not be valid anymore. So I'm excited, friends. Let's get rolling on some symmetry. Let's see, what do I got here? Oh God, I gotta remember. I have to have you do this pre-test. It's like no grade, but it's for assessment. I don't like having to do this stuff, but my department makes me. So eventually, we'll stop like about 15 minutes early, and I'll just ask you to do your best on this, and at the end of the semester, I'll ask you to do it again. But, yeah, you've done this before,
Yeah.
Yeah, cool.
Just stare at a pretest, I have no idea what to do.
Yeah, and that's great. Honestly, that's great because then you're totally improved when you write something at the end. So yeah, no pressure. No pressure, no, yeah. Anyway, it's Dr. Patnott, so it should be interesting and challenging, but doable. She's good like that. Alrighty, my friends. Maybe let's just do a quick bit of bureaucracy. I'll just talk it through. The syllabus is up in world class in the content area. My office hours are up there. Here, I'll just pass this around. This is kind of you can see my office hours there. Monday, Wednesday, Thursday, and Friday. On Thursday, they'll probably be by Zoom. I'm happy to set up appointments with you whenever. So you just, it might be Zoom, but we can meet whenever you'd like to meet, and we'll make it work.
Yeah, I'm a soccer player here, so
Okay.
My fall is really crowded, especially these next 2 weeks. But yeah, we can talk more about that after.
Yeah, Kyle, we'll, just keep me in the loop on what that's gonna be, and then if you wanna talk about anything, we will absolutely work it out. Cool. So, not a problem. You guys are my special crew, right? Like, I'll do anything for you, and we'll meet anytime, whatever you need. Not that I don't love everybody else. Let's have more fun. I'm not ready to put a theorem up yet. Not that that's not fun either. Oh God, okay, come on.
Yeah, these boards suck. They're the computer ones.
They're not good, I've got these beautiful black markers that I bought myself, and you've all heard me go through 2/3 of you have heard this shtick constantly in class, so, is there any questions on anything before we go? Homework assignment. Yay! Yeah, fun one. So this will be due let's shoot for the start of class next Wednesday. Kyle, you'll find that things contract and expand in my classes depending upon what we need. Okay. So they had this new thing where they were like, put all the assignments in world class and the dates they're due, and I was like, I don't fucking know what we're gonna do. I just figured this out this weekend, and I don't know when the next one will be, and I'm not going to. That's one of the joys of being a full professor. No, I won't be doing that. Okay, so this will be due Wednesday, the 31st, start of class. What? End of day. God, end of freaking day. If you turn it in end of day, I'll make a Dropbox and you can just scan me a PDF, please. So this is homework 1, it's chapter 0. We will actually spend most of this week on chapter 0, just getting warmed back up. But it's going to be 2, 3, 4, 7, 14, 37, 38, and there's 8 problems in total. And here's a custom one. So also find 5 to the 1,000th power mod 4 and 4 to the 1,000th power mod 5. You won't want to use a calculator on that. There'll be better ways to do that we'll talk about. So let's go back into symmetry, bit. Oh, and these two friends know it, but Kyle, what I would ask that you just, at least for every problem, include enough of a problem statement that I know you know what you're solving.
Okay.
That anyone who picks it up knows what's up. Okay, so let's take a look back to symmetry, and let's get deeper into this. Let's imagine we have maybe some molecule that looks like this. Let's go back to that nice molecular structure thing, and this is all supposed to be the same. All these lengths are supposed to be the same. And everything is supposed to be so that if I rotate this thing 120 degrees, it lands back on itself. Let's work with that. Let's get some labels here. We got A, B, C. So let's talk. We just went through all of this. We've got rotations. And we've got how many? How many rotations? 3. So the first one is I don't rotate at all, or I rotate 360 degrees and it lands back on itself, but let's just call that R0. I've got R120, and then I've got R240. And let's also indicate the direction of rotation so that we're clear on that, because we're gonna label some things here. So if I do R0, I've got a picture of it right there, but let's put a picture up of each state after that rotation. And then for R120, the B is going to be on top, C is going to be down here, A is going to be over here, and then for R240, we are, the C's on top. Got those 3 states via rotation. And then we've got flips. And we're gonna think of the flips like this. I wish I had my multiple colors now, because I would like to draw how we're gonna do flips. Let's call that flip A, indicating that the A point is one of the points on that flip line. And then you can kind of see we're gonna have flip B and flip C as well. So this will be flip B, and then this will be flip C. And so let's make pictures after those flips of the state of things. So let's see, so after flip A, C and B change positions, but A stays fixed. Can I get this by a rotation? This flip thing? Is there some way I could rotate to get this state? No, right? No. It's an orientation change, and there's just literally no way I could rotate it in the state. So that's a very unique thing. So this is flip A, and then flip B is going to make C on top. Oops. A down here, keep B fixed. Flip C, you know what that's going to do. It's going to flip A and B, fix C. So let's flip C. And now what we're going to do is make a table. And I made a lot of these this summer, and it's soothing. And I know that this is going to sing to your heart because you're math people. And this is just pure beauty. What we're going to do, we're essentially going to own all the possible symmetries of that thing and understand their interactions with each other. So here we're going to make an operation table. And the operation is going to be composition of these basic motions. So one following the other. So here, I'm just going to put a little bit here. This is composition of basic motions. And this is going to be the first one. So this will be the first, and then it'll be followed by this one up here. May be that order doesn't matter, but we don't know that yet. So let's be clear about it. I'm going to go through and list the 6 basic operations. And I'm going to do that across the top. And now I'm going to fill in the table. We can let's do some of the low-hanging fruit together. R naught is essentially the identity here. Let's maybe even make a little note of that. This is kind of the identity. It's like multiplication by 1 or addition of 0 doesn't do anything to the next action. So that means if I first don't do anything and then I do one of these things, I just do that second thing. And similarly, if on the second time I don't do anything, R naught, I just did the first thing. What happens if I do R120 twice? So I do R120 and then R120, what do I get? R240. Exactly. And the answer is always one of the basic operations. Is this making sense? How we're going to roll this? So let's just do this second row together. So first I rotate 120 and then I do 240. Where am I at, Diana?
360.
360 or R0, right? So yeah, exactly. So that takes us back to original state. What if I do R120? Now you gotta be careful here, and that's why you need these pictures. So first we did R120, so we're here. And now I'm going to flip over A. So when I flip over A, so here's R120, and I follow that by flip A, what I get is A fixed, but then C and B changing positions. What single operation would accomplish this? Look at the table, like what single operation gets me the same effect? All right, so R120 looks like this. I think, is that right? No, wait. Yeah.
Yeah, you're right.
Yeah, okay, yeah. I forgot, I was rotating the other way in my head. So R120 gets me here, and then I do the flip over A, it flips these two. Notice that that is the same as a flip over B. That the final state is accomplished by just F of B, so that's what goes right here. What's the next one gonna be? R120 followed by flip over B. Flip over C, yeah. Do you see that? Diana, is that making sense to you?
Yeah.
Yeah? So let's flip C. And now, because we're math people and we understand patterns, we kind of, even if you didn't know, what would you guess went in the last slide? FA. But let's just verify it. So do R120, then flip over C. So there's R120, but then I flip over C, and so that flips A and B. So I'm going to have C, B, A, like that, and that is flip A. Can you finish this table, please? Because you got to do this once in your life. Today's a good day. I'll slowly go through too, so that you kind of get some sanity checks. Oh, I think I was doing the wrong one. No, I think that probably is right. Did I do it? R240 and then flip A. Oh yeah, ABC. Yeah, okay, that's good. And then R240 flip B is gonna make BCA. I'm gonna cheese out. Keep the order in mind when you get down to that fourth row, you're flipping first, then rotating. So we're gonna do flip A and then R120. So that puts A, C, B like that, and I just look for that pattern here, and it's flip B. If you see me doing anything you disagree with, speak up, please. Lots of eyes on this stuff. Total cheat. Oh, and there are some easy ones as well. You know that flipping, doing the same flip twice restores order to the world. Just kind of cheese out. You're already done. You got it. Oh, nice. You're cooking.
I just found the pattern in the table and then the extrapolation.
Yeah. There's also that. Just gotta be. Yeah. You gotta be careful, but I think you're probably onto it. So let's see here. So flip A and then flip B. That's fun. Flip A and flip B gets me B, C, A. So that's a rotation. No. Wait. Did I do that? Yeah. Flip A. And flip B. What?
It's R240.
Oh, it's R240, thanks. Okay, yeah, oh, it's right there. Yep, gosh. R240. And then I'm totally gonna just rely on the goodness of the world. That each one of those things has to appear in every row and every column exactly once. Flip B, what'd you get for flip B, R120, Kyle?
Flip C.
Flip C. And then flip B, and this probably flip A?
Yeah.
Right, next one. And then this is flip B, flip A. What'd you get for that guy?
Flip A. It's B, C, A. R120.
I'm gonna do that cheese. My table's a little whack. That's what's wrong there. Okay. A little skewed. Then this has to be flip A. And then this has to be flip B. Let's see, so now look at that. That's got to have one of everybody, so that must be R240, and that must be R120. Seem reasonable? Let's just make sure everybody feel good about this. Now, I'm a little unnerved for the simple reason that I didn't think this table was symmetric about its diagonal. And that's disturbing me a little bit. So I'm just gonna double check a couple of things here. So flip C followed by R240. Here's flip C, and then R240 gets me to A, C, B, and then that is flip B. So, okay. Yeah, okay, I get, that's something to notice here. Am I looking at this properly? Oh wait, it's not totally symmetric, is it? There's a bunch different, aren't there? Like these guys here.
Yeah.
Okay, so the outer edges are not even identical. Oh, cool, good. That's real good, because I didn't think that should happen. So it's just my my day one eyes apparently looking at this. So notice that there is no symmetry here on the diagonal. In other words, it matters in which way I do the operations. So here, order matters. And we'll get to this a little later. In other words, this is non-commutative. We're so used to A times B is B times A, but it's not in this world, and it's not times either, right? It's a much more complicated, abstract operation that's going on here, but it is non-commutative. And so to indicate that, all I have to do is show one place. So let's see, what's a good example? We've got, so FC times FA. So, okay, watch how I write this. This was the first thing. Here's the second one. So this is first, and then this is second. Now, why am I writing it like that? Because I'm thinking of these things as operations. They're acting on something. This is acting on this. Yeah, so it's like matrices. When you do matrix multiplication and you've got matrix A times matrix B, this one is eating that one. So things are moving to the right. They're chowing to the right. So this is not equal to the other order. And this dot right here is not, I'm gonna make it like super weird looking. It's not multiplication. So we understand a lot now about the symmetry of that thing. And we actually own it completely. We understand how to compose any two of those operations. And then look, there's another layer of symmetry to look at here. We are literally looking at the symmetry of the symmetries. And there isn't a symmetry of the symmetries. There's this wonky symmetry in some ways. So this is actually our first example of a group, which we'll get to in about a week. What's called a group. I've got a single operation on a set. So I've got a single operation. I don't know what that operation is. It might not have anything even remotely accessible geometrically on a set. And the set is, we're closed under that operation. Put these things here. And every operation has an inverse. Every operation has an operation I can apply to it to get back to the original state. So what I mean by that is, and let's actually put that up here. And there's a couple other little subtle properties we don't need to get into today, but this is the heart of it all. So every operation has an inverse. And let's just write this out so that it's in your head. Oh, this carpet is just foul. I was gonna lay down on it, but I think I'll bring a cot next time. Yeah, that's the kind of mat to put down here. This is just, no. So for example, if I take, let's try to find a good one here. Well, I was trying to find an interesting one, but they're all okay. If I take R240, its inverse element is equal to R120. So I use this little notation here. Usually that means reciprocal. For us, it means just inverse. Kind of like, and matrices do this too, right? You put a little -1 for inverse. So this just indicates inverse. And that's because R240 times R120 gets me this R0. And this is the identity element that I mentioned before. It's the one that doesn't change anything. So check this out. There's nothing to do with multiplication here. This is all geometry. and it's all about symmetry. And this group has a particular name. This is actually called D3. It's so common that it's actually got a name, and it stands for dihedral group on 3 elements. It is the same as the symmetries of an equilateral triangle. So notice that symmetries, and I kind of cheat, right? I like pulled it away. I didn't want it to look like a triangle, but it's a triangle. So, yeah, symmetries of a beautiful equilateral triangle. Get the same thing. Yay. Any questions at all on that, friends? A few minutes here. Got time for one hardcore thing. This is all pretty chill, making sense, and yeah, awesome, outstanding. This is the heart of abstract algebra. And then we're going to get in there, we're going to have much more complicated group structures and stranger things, and we're going to get in and understand things that appear inside groups and the ways they relate, and we're just going to like understand symmetry in a way we never did before. Welcome to abstract algebra. Hope this sounds fun. Like I said, different. Yeah, really different. It's going to get a little weirder here. Is it okay if I erase table? Yeah. Great. It's going to get a little weirder today.
It was awful.
What's that?
The lack of erasing.
Oh, it's pretty hideous. I'm going to have to bring in my own supplies. I actually heard that, or I think I saw it on TikTok, like if you take WD-40 and treat your boards with WD-40, I might do that. I'll bring in some WD-40 on Wednesday. We'll hose this thing down with it. Yeah, truly ghastly.
It's just gonna get worse with the black markers.
But my black markers are still high quality.
I know, but the boards are so low quality.
It's true, but we're gonna WD-40 literally fixes everything.
That's true.
I don't know if I'd go that far.
You can make it fix anything.
What can't you do with it? Well, there's a lot you can't do, you're right, Kyle. Okay, so there are some essential tools in our class that are alien. And they're going to feel alien until you use them a lot. And you will use them a lot. So this is chapter 0. That wasn't chapter 0. This is chapter 0 we're going into. Fundamental tools that we will need. Fundamental tools. We'll take the time we need to understand these tools and to implement them. And the first one, I'm not going to prove. This could be proved. I think you're going to accept it once we talk about it. The well-ordering principle. Anybody ever heard of this? Maybe in logic and proof? Yeah.
That was a while ago.
It was, I'm sorry, yeah, it truly was. So, well-ordered principle says this. Every non-empty set of positive, every non-empty, let's say subset of the positive integers, just to be a little bit more precise. And I'm going to introduce the symbol just in case you haven't seen it in a while, because we'll use it a lot. I use the integer symbol with superscript plus. So this is just, 1, 2, 3, up. Every non-empty subset of the positive integers has a least element. You give me a collection of positive integers, no matter, even an infinite one, it has a least element. Think about that for 1 second, because I'm gonna try to complicate it in just a second. Does that make sense to you? Why that is so? Believe it or not, we can prove that.
Just gonna stop at 1, can't go any lower.
You can't, there you go. Can't go any lower than 1, right? But maybe even a little subtler than that. What if I change z? Is this true if I instead say the positive real numbers? What if instead of z plus I say the positive reals? Is this true for that set? Here's the positive reals, and some people in here have had real analysis. It sure seems like a question about the reals, because it is. So there's those. Does that set have a least element? This one here, the actual set that we're starting with? What's the least element?
How to quantify it? No?
No, it doesn't. So explain. Trinity, explain.
I mean, the way I think about it is, so zero's not in the set. but
Right.
Like,
Right.
say, you're like, okay, so the least then would have to be like 0.001, but then you have like 0.0001.
Yeah, yeah.
And then you keep going,
Yeah.
going, going.
There's always, you can always have, whatever you claim it is, I'll take half of it and it's in there. So this set itself doesn't even have a least element. And it'd be pretty easy to just pull out other subsets of it that are just open on the left side like this. What about the rationals? If I just use the positive rationals. Positive rationals. So you get Q plus. It's just the fractions in there.
It's the same thing.
Same thing, yeah. You say, wait, there is a smallest fraction. I know damn good and well it's 1/1000. Well, you failed, because there's 1/2000. So no matter what you say here, there is no least. So this is obvious, but not trivial. And it really depends on this set that we've picked right here. What about the whole integers? What if we remove the plus? It's still true. Any non-empty set of integers has a least element. Kyle, you were kind of onto it with your very first comment. But give me an example of a set of integers that's non-empty with no least element. How about the negative integers? Right? This set right here. Dot, 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 that there, right there, you know. Not those non-positive integers. There's no least element in there. So like what you said at the beginning, Kyle, you're like, there's one. You can't ever go to the left of one.
Yeah, with the positive.
Yeah, with the positive. So that was super key to this. So there's two things that are key. One is we've got this stopping point, ultimate stopping point, and the other is there's not a lot of granularity here. It's pretty discrete. They're chunks.
Yeah.
They're not too close together to cause.
Are the best numbers to have?
They're not going to cause infinite closeness problems. That's real analysis. That's what real analysis is. Infinite closeness problems. Okay, so we're probably not going to get to the main theorem, but I just want to introduce two more definitions and then give you a little bit of time to do whatever it is you want to do with this thing here. So here's a basic definition, another key, essential definition, every freaking day. Every freaking day, every problem almost. So definition, given two integers a and b, does that make this all, sorry, that's my element symbol, I'll translate for the first few days until I get used to it. So they're integers, elements of the integers. We say, and let's say here that a is not 0. We say that a divides b if there exists an integer k such that b is equal to k times a. Some multiple of a gets me to b. Yeah.
It's just a big part of logic.
Absolutely. And this is like your first part, right? Because I taught that class out of the same book.
Yeah.
This is like one of your first definitions. So let's just get a couple examples here. We know that 17 divides 51. Literally one of my favorite like number pairs, because it's just so weird that 51 has a factor at all. 3 times 17 is 51, but 5 does not divide 51. But let me point something out here. There is something interesting going on. It doesn't divide it, but I can express 51 in terms of 5, and this is going to lead into what we'll start on Wednesday. But 51 is equal to 10 times 5 plus 1. If I had a plus 0, then I would have, like here I've got 51 equals 3 times 17 plus 0. There's like no remainder when I divide. When here I divide, I've got a remainder. And this leads us into probably the most fundamental tool called the division algorithm. Didn't you talk about this in Logic Improve?
Yeah.
Awesome, awesome. So we'll just pick up there on Wednesday. And what I would recommend, if you want to read ahead, you could start reading through chapter 0. That's just not going to hurt you in any way, shape, or form. This book is pretty well written. I think it's a good read. But definitely, pick up from there just to get a little prep up ahead. I'll tell you what's coming. So we're going to talk about the division algorithm and greatest common divisor. If you read just those basics, you'll be really ready for Wednesday. Thanks for a good first day, friends. Awesome. Here is your pre-test.
Write the name on it?
What's that?
I said write the name on it?
Yeah, sure, yeah, absolutely. At least make it a very fancified version of your name. Some effort in there, Kyle. For God's sakes. Do what you can on this. There's no judgment. There's no grade. And if you write nothing, there's only up to go. You can only get better.